Okay, so up to this point we've been talking about, for the subsurface environment, we've been talking about movement in groundwater. So now we're going to talk a little bit about movement in unsaturated soil. So this is all that stuff above groundwater. So what is that stuff? That stuff is all the organic matter, things that live there, biota, microbes, vertebrates even that we talked about that live in the surface soils. So it tends to be more of the organic matter, more of the weathered material like clays. You'll also hear it called the vadose zone. I'm not going to talk about it using those words too frequently here, but it's just so that you know what it is if you run across somebody saying that. It's just the unsaturated zone. Okay, so once in the unsaturated zone, a pollutant can vaporize into the atmosphere. It can move downward in soil water even till it reaches the groundwater. It can absorb to humus, organic matter, or clay. It can degrade, and mostly we're talking about biodegradation in a soil environment when we're talking about degrading. Or it can be taken up by plants, and we'll talk more about these last two particularly in when we talk about bioremediation efforts. Okay, so this video is going to talk about how pollutants may or may not vaporize into the atmosphere from soils. Okay, so in general, we've talked a lot about pollutant characteristics and what characteristics make a pollutant want to go into what state. So here's more along those lines. So compounds with a high vapor pressure, they tend to be more volatile, and that's a vapor pressure typically greater than 1.3 times 10 to the negative third atmospheres is considered to be a relatively volatile chemical. In soils, you want something with a high vapor pressure but also a low water solubility to make it vaporize into the atmosphere. So you need something with a high water solubility and low vapor pressure is not going to have a very high probability of volatilizing from the soil. Okay, so here we have three chemicals. We have benzene, perchloroethylene, and pentachlorophenol. And you can see the vapor pressures of each one of these. Benzene here, 0.125, 0.02 for PCE, and pretty low for PCP, or this pesticide. And different values for water solubility. You can see also decreasing across these chemicals. And the KOC, so this is the partitioning coefficient between organic carbon and soil water, increasing. Okay, so which of these would be most likely to end up in the atmosphere? So here you have essentially two volatile compounds and one non-volatile compound. So you could think about either one of these, benzene or PCE, as being sort of candidates for volatilizing to the atmosphere. Okay, and then we can think about which one of these is going to absorb to the soil most strongly. Benzene has pretty low absorption, PCE has moderate absorption, KOC of 665. Pentachlorophenol clearly has a really high capacity to absorb to soils. And which would most likely end up in groundwater? That's going to be looking more at sort of the combination of vapor pressure and water solubility. Benzene is incredibly water soluble, perchloroethylene is less water soluble, and PCP is only slightly water soluble. So in thinking about which of these chemicals is going to end up in which phase, it's most likely that the PCE is going to volatilize. It's not very water soluble but has a relatively high vapor pressure. Not a hugely strong potential to absorb to organic carbon. PCP has a really high KOC, so it's most likely to end up stuck to soil, absorbed to soil, whereas benzene is really considered to be really highly mobile to groundwater. Even though it's got a pretty high vapor pressure, it's also got a really high water solubility, so it tends to end up in water more than in the atmosphere. Okay, so other things that impact whether or not a chemical ends up in the air. So it's not just the properties of the chemical, it's also the properties of the soil. So things that we've already talked about matter, things like porosity, how much pore space is there, and then permeability, how connected are those soil pores. And that's going to matter for whether or not a chemical can travel out of the soil and into the atmosphere. It needs connected pores to do that. So a couple things impact the ability of a gas to travel into the atmosphere. So not only the connectedness of the pores, but whether or not they're filled with water. So if they're filled with water, a gas is going to be much less likely to get from the soil into the atmosphere. Okay, so here's a question you can think about. Which of these two soils, and you've seen this picture a few times before, which of these two soils, they're the same soil, one is compacted, one is not, would have greater gas exchange with the atmosphere? So you can pause the video if you want and think about that for a moment. Okay, so this soil over here has more pore space, more connected pores, so more capacity for a chemical to make it out of the soil and into the atmosphere than this one, which has much smaller pore space and more compacted pores and much fewer connected pores. So it would be much more difficult for a chemical to make it out of this compacted soil. Okay, so there are a bunch of sort of familiar looking equations that computer programs and other people can use to estimate rates of vaporization and how much of a chemical would make it into the air. Things like Fick's law, which we've talked about several times before, to estimate flux using a diffusion coefficient and concentration gradients. And then there are also sort of mass flux or convective flows that are sort of functions of pressure gradients. So these are things like changes in atmospheric pressure due to barometric pressure and wind gusts over the surface, or infiltration of water into soil, which can force air out of soils because it's being replaced by water, and changes in the water table. So a rising water table could force soil air and soil gases out. This is one equation that people use to try to look at convective fluxes. And I'm not describing these in detail, essentially, because I'm going to tell you that using these familiar equations is really hard. So these conditions are always changing, right? The weather is changing, water tables fluctuate, it rains, and soil moisture changes. So these are things that we need computers to do. So in this class, we're just going to think about this relationship. So this is something that Dow researchers found an empirical relationship to find a first-order decay rate of volatilization, or for contaminant loss from surface soils to air, that looks like this. So the Kv is this sort of decay rate or volatilization rate constant, and it's a function of a constant, it's 4.4 times 10 to the 7, times vapor pressure, divided by KOC times water solubility. So you'll notice all of these units are different, right? No weird units, but you're still going to end up with a rate constant of per day if you use these units. So the conversion and all of those things that need to happen are sort of sucked into this constant here. So you'll need to remember that even though you're using these units that don't come out to 1 over day, your Kv is still going to be in the correct units. Okay, and then here's an example that I'm going to do for you guys in a separate video. Okay, so this is summing up. So for vaporization from soils, of a chemical from soils to the atmosphere, using those familiar diffusion and pressure gradient equations is pretty difficult. So in this case, we're just going to use this empirical relationship here based on vapor pressure, KOC, and water solubility to get a first order decay rate, which we then put into this equation. And I'll have an example showing you this. It'll make it a little bit clearer exactly how that happens. And then I just want to mention that for deep soils, things are even more complex, including the models. So that's something that a more advanced class needs to deal with. Okay, so then the last video is going to deal with how chemicals move downward in soil water, or how they move with soil water.